All right, in this video, I'm going to show you how to sketch some simple two-dimensional vector fields. So after sketching each field, then we're going to, by inspection, determine whether the field is expected to have divergence and curl or not. So remember, we said divergence is a matter of how the field spreads out, and curl is a measure of how the field curls around a point, whether it's got some rotational tendencies. So in the first example, we have got f equal to 2i. So this is a constant vector. If I write it in column form, this is 2, 0. So it means at every point on the xy plane, this vector is just going to have an x component of 2. So x component is a horizontal component. So if we take the vertical axis, for instance, so basically it doesn't matter wherever we are. I'm just going to take a few points along the vertical axis. So that means if the x component is 2, the y component is 0. So this is always going to be magnitude 2, irrespective of where we are on the xy plane. So this is what we're going to have here. So this is going to be a constant flow in the x direction. The magnitude of each of these is going to be 2. So that's going to be the shape of this vector field. Going to part B. In part B, we have vector field I plus xj. So for this one, the x component again is always going to be constant. It's going to be 1. But the y component is going to be given by the magnitude of x. By the way, for this vector field, there is no indication of spreading out from any point, and there's no indication of any rotational tendencies. So for this one, we expect both the divergence and the curl to be 0. Right, so let's have a look at this one. Now, whenever you have got a vector field that involves x and or y, then the first point to start with in terms of the sketch is the axis. So for instance here, we're going to start with the axis along which x is 0. So along x is 0, this thing is always going to be giving us this vector. So that's going to be a constant vector, similar to this one we just did. So this is saying along the vertical axis, this is what we are going to have. And in fact, so because here is the x is the only variable, it means if we choose a vertical line, we're always going to be getting the same vector. So suppose now we go to the point, imagine this is the point 1, 1. So x is 1, y is 1. So if we plug it in here, it's now going to be giving us the vector 1, 1. Vector 1, 1 is saying we have got 1, magnitude 1 in the x component and y 1 in the y component. So the resulting vector is going to be this one here. Now, along everywhere on the vertical line x equals to 1, the vector is going to be similar because x is the same. So if we choose the point 1, 0, if we feed it here, still it's going to give us the same vector because we are plugging in 1. This one is always 1. So again, we're going to be getting that 1, 2, the same vector. So this is what we're going to be having all the way up and down that vertical line. Then now if we go to the line x equals to 2, so this is now going to be 2. So we're now going to have 1, 2. So the horizontal component is still 1. The vertical component is now 2. So that means the vector we're going to be getting now is going to be a bit longer. And it's going to have more inclination. So along all the points along x equals to 2, we are going to have this type of vector here because x is the only variable here, and along here, everywhere here, x is 2. That means even there we're going to have the same vector, a bit longer than this one, and a bit more inclination. Okay, and then I think you can see that if we go further to 3, then we're going to find a vector which is even longer and more inclined. So that's going to be how that works. Now let's go to the left hand side of the origin. So suppose we take a vector here, a position where x is now -1. So remember the x component of this vector is always 1. So it's just the y component, but the y component is given by x. So now we're going to have 1 and -1 here for this vector. So that means the x component is still going this way because the x component is still 1, but the y component is now going this way. So that means our vector is now going to be going this way, and this is the vector that we're going to be getting for all the positions along x equal to -1. And then if we now go to x equals to -2 here, this component is still going to be 1. This component is now going to be 2, but negative. So this is now going to be a bit like this. So that's what we're going to have. And then these ones are going to be like that. So you can see that at the end of the day, if I can just make a fresh sketch here, what we are going to have is a vector field that is going a bit like this. So along here, nice and horizontal, then starts going up a bit, and then as you go further away from the origin, then your vectors are going to be, magnitude is going to be increase, and the angle of inclination is also going to increase. And then this side, this is what we're going to have. And then again, as you get further from the origin, the magnitude increases and the angle of inclination increases. So that's going to be what the sketch of the second one is going to look like. Now, going to part C. Okay, before we continue, what is going to be the situation with the divergence of this? Now, since the magnitude changes as we go away from the origin, if you take any point here and make a closed circuit, then you find that the elements coming in this way will be less than the elements going out this side. So that means there is going to be some kind of divergence that's happening here, because as you get further from the origin, the magnitude of the velocity changes. And then since there is this obvious change of direction, so again there's going to be, this is indicating some rotational tendencies, and so the curl we expect for this one to be non-zero as well. Okay, for part C, we've got f is equal to xy. So this is part C. F is equal to xy. This is just the position vector of position vector r, this one. So it means wherever we are, the vector is just going to be given by the components of the xy coordinate for that point. So again, this involves x and y. So if you start with the coordinate x's, so for instance, along this axis, x is 0 here. So that means this is going to be 0y. So that means the vector is always going to be in the vertical sense, and its magnitude and direction is going to be given by the magnitude of y. So if you are here, y is 1, so our vector is going to have magnitude 1. And then the next one is going to have magnitude 2. And then here, y is negative 1, so it's going down. And then the next one is going to be given by 2. Then now, if we're along the horizontal axis, along this axis here, then the vectors here, x is 0, no, y is, along this axis y is 0, so there's going to be x 0. So the vectors are going to be horizontal, the magnitude given by the value of x. That means as we get further and further away from the origin, these vectors have got bigger and bigger magnitudes. Okay. Then, for instance, if we take this one, 1, 1, at 1, 1, we're going to have x component 1, y component 1. So it means our vector is going to be along the 45-degree line. And then as you keep going this way, it's going to become longer and longer, that vector. So in fact, this is what you are going to get for this position vector vector field. So this is just going to be depicting a vector field of a source at the origin. So if you just have a source at the origin, and then all your streamlines are going to be moving away from the origin. Any rotation here? No rotation. Any sense of spreading out, divergence? Yes, there will be some divergence, obviously, because you've got a point source right at the origin here. Okay, then the next one we have f equals to y negative x. So f equals to y negative x. Again, this one, since it involves x and y, we're going to start our sketch along the coordinate axis. Okay, so for instance, along this axis, x is 0. That means along this axis, this is going to be given by y 0. And then along this axis, y is 0. So the vector will be 0, negative x. Now, this vector here is always horizontal, and the magnitude is given in the direction by y. So for instance here, y is 1, so that means this vector is going to be going like that. And then if you go up further, y is 2, so that means that vector is going to be going like that. And then below the the origin, y is now negative, so it's going to be negative 1 here. So it's not going to be going this way, opposite to that one, and then getting bigger as you get away. And then here, x is 1, y is 0. Okay, x is 1, so it's going to be 0, negative 1. But this negative 1 is the vertical component. It means here it's going to be going like this, and then as you get further, it's going to be getting bigger. Here, x is negative 1, so it's going to be negative 1 here, so it's going to be 0, 1. So it's going to be going up and then further. And then just from this, I think it's showing you that generally this vector is going to be a concentric type of vector field. Movement being around the origin, so the intensity or the magnitude of this vector field grows as you get further and further away from the origin. And clearly there is a rotary movement here, so the curl we expect to be 0, and since as you get further and further the magnitude grows, we also expect the divergence to be non-zero. Okay, we are now going to give you a chance to have a go at these vector fields here. Let's have a go at these vector fields, and then if you want to compare with our drawings, you can pause the video and then all right, so this is how the vector field minus j is going to look like. It's just a steady flow down, magnitude 1. This one is going to be having this general direction of flow. Then G, this one is going to be going in and out like this, and also in and out like this. All right, thank you.